Thank you for joining us to be an engineer for a day with Heriot-Watt University. And today we're going to be focusing on aeronautical engineering, to be an aeronautical engineer for a day. We do so because it's such a wide industry, and it's one that has so many opportunities and so many challenges. It is an industry that has transformed how we live and how we work for the past 100 to 200 years. It connects us. It connects us with people around the world, and it also helps industry to move goods and services across the world in very short periods of time. And while some of the fundamentals of principles of flight have not changed, the industry is constantly evolving. And there are challenges here for nearly all engineers. Mechanical engineers, we might be more interested in the powertrain, the big jet engines that power these huge aircraft today. And we might also be interested in the fluid mechanics, how fluid flows over the airfoils, over the wings, that give it lift. And that'll be the focus of today's task. But there are so many more opportunities for those who are interested in perhaps electrical or electronic engineering. Avionics is a whole discipline of itself. It is all about the signals and sensors and how we communicate across the aircraft itself. There are hundreds of kilometers of wires in a modern aircraft. But there are other challenges there too. The fuselage itself, this large aircraft, is a structure. So you will find civil and structural engineers working in the aerospace industry. And one of the major challenges that is facing the aerospace or aeronautical engineers of the future will be decarbonization, the decarbonization agenda. So there are chemical engineers that are looking at developing net zero carbon fuels. So these are some of the challenges that engineers have to do today. So what are we going to be focusing on? Well, we'll try to give you some insights into the powertrain. I'll be taking you through some of the fundamental principles of a jet engine, something like this. Mohammed's going to look at the avionics, some of the challenges to do with electrical control on a modern aircraft. And then Mehdi will be taking us through some of the fundamental principles of flight, where we look at the fluid flow that goes over an aircraft wing and how that gives us lift. So where am I today? Well, I'm in Al Mahata Airport Museum. It is a wonderful place that celebrates the history of flight and some of those fundamental principles. It looks to today and the current industry, and also a little bit looking to the future. Here in the museum, they have this amazing cutaway of a jet engine. And it allows me to show you some of what's happening as we go through the engine. So at the beginning here, air is shrouded or guided into the first section. This first section essentially is a compressor. And its whole function is just to compress from ambient pressure to a much higher pressure. So as we go from section to section, the pressure of the air is increasing all the time. And that's going into these combustion chambers. Now, these combustion chambers are arranged around the circumference of the central core of our jet engine. And in those combustion chambers, you're going to have high pressure air. We'll then inject jet fuel into that combustion chamber, and straight away the temperature is going to rise. It's going to shoot up to maybe 1700 degrees Celsius. So now what do we have? We have high pressure, high temperature air leaving at this section of our jet engine. And that goes through here, it goes through a relatively small turbine. The sole function of this turbine is to give enough axial power, enough power to turn the axis of this jet engine so that the compressor can do its job. So that then leaves us here still with a pretty high temperature, pretty high pressure jet of air that's going to gush out, going to fly out the back there, and it's going to give us that propulsive force that makes our jet engine go forward, and of course attached to the aircraft, giving us that power that you need for takeoff and for flight.
Moving into modern aircraft, here we are in TFT Aero in the JDR Dubai, and this 737 next generation. This is more of a modern aircraft, and you can see the use of screens together with multiple panels to communicate information to the pilot and the first officer sitting next to him or her. Talking about avionics in general, what we are trying to achieve with all these panels, which look rather complicated and overwhelming when you first come in, but I can guarantee you it gets a bit simpler than it looks as you finish your type rating and get familiar with the aircraft. These are laid out into different panels, which is basically depends on what you want to achieve, either navigation, control, or performance. View information related to your navigation, as you can see in these screens, communicate to the other airplanes and the aviation control. Also get information about your engine performance, your fuel, and manage to control everything in the airplane. Control can be done obviously manually, but a great deal of control goes here with the autonomous autopilot, which is rather sophisticated, that use a mix of electronics and autonomous systems to get the airplane from point A to B at different altitudes, points that are thousands of kilometers apart on its own. But that takes lots of engineering to get into that. Talking about what you have to do here, linking it to our task, obviously, as you fly, you will need to control a few different things in the airplane, rolling, and your yaw and pitch as well. And that done with introducing the thrust, lots of turbo machinery in there. But let's talk a bit about wings. And as you look into a wing, and if you have been ever into that wing window seat, might not look fun, but maybe not the next time after you finish this task. The wing is there and it's fixed, but you want to change how much lift you get out of that wing, and we will get to deal with that in today's task. So you look into introducing surfaces like flaps to change area and camper, and don't worry, we'll get to that terminology very shortly. And that will change how much lift or less lift you get from the wing, which will adjust the airplane. Now, something else which you want to do is sometimes the flow over the wing is very good, but you want to spoil it a bit, and that's what the spoiler does. It spoils the airflow, and that will affect the lift as well. A combination of these and many other basically devices that goes all the way to the tail of the airplane with the stabilizer allow you to control the flight. That control is done in here and can be done autonomously, but also there are additional systems that allow a pilot and the first officer to overcome difficulties, system jams, system failures. When you fly, you want to keep flying. So within the aviation industry, there is always systems, subsystems, and additional systems to stay, to help the pilot to maintain flying. So for example, here you control your flaps and adjust their positions as you move. And here you get the control all the way to the lifters and the stabilizer. And there is a physical connection using a cable. So if you have to, there is actually a wheel which you can turn, but that's only in situations that require that. So if you have seen any cockpit videos, you will see these all the way adjusting themselves with the autopilot and many others. So this is only possible with a combination of electronics, autonomous systems, lots of wiring, sensors, combined with mechanical system to come to such a complicated system to work together. Your task today is to make use of all the thrust available to you within a speed of flight to adjust your area of your wing and get the lift you want. So enjoy the task.
Hello, my name is Mehdi Nazarinia. I am an associate professor in mechanical engineering. I've got a background in aerospace engineering when I did my undergraduate studies, and I also have a master of aerospace engineering, but specialized in aerodynamics. So this will be my pleasure to introduce you to our task for this aeronautical engineer for a day. When we are going through airplane design process, we realize we are dealing with balance of different parameters, which are at the same time very demanding, and also they're competing each other as well. So for us to be able to design and build strong, lightweight, economical, and at the same time safe airplane, we need to basically balance these factors. So you have heard about different subfields of aerospace engineering or aeronautical engineering. One of them is aerodynamics, and that's what we are going to be concentrating on in this episode. So aerodynamics is the study in general of the motion of air around a flying object, like this wing, for example, right? So the interaction between the air that goes around the wing of an aircraft with the surface is basically what is studied under aerodynamics. So there is a solid object involved, or airplane, and there is a fluid involved, which is air in this case. So that's why it's called aerodynamics. Before we jump into the actual task, just to ensure all of us are familiar with the terminologies that we're going to be using in the tool, I'm going to be taking you through some of the common terminologies that we use. As you can see in this slide, airplane has different parts. The main ones we're going to be concentrating today is fuselage, which is the main body of our airplane. And then the wings, which are basically responsible to generate an upward force for us. Okay, so wings are basically designed in different shapes and forms. Today, we're going to be only concentrating on one form of them, which is rectangular wing. I'll go and show you a schematic very soon. But from every other part that aircraft has, today we're going to be only concentrating on the wing, which is going to be attached to the fuselage, where it's carrying passengers, payload, even sometimes fuel or cargo. So that's what we're going to be concentrating on. There are different phases of flights that an aircraft or airplane is going to go through. Starting from taxiing, for example, let's consider a commercial aircraft. Goes through taxiing, then takeoff, cruise, descend, and then landing. So for long-haul airplanes, the main phase is going to be the cruise phase. This is where they're going to be climbing at a certain altitude, keeping that altitude, and cruising to the destination. So for an airplane to be able to move from point A to B in a certain altitude, all the forces has to be in balance, like what we're showing here. So the two forces that they're going to be opposing each other are the weight, which is the obvious one. It's, the airplane is made of solid material, so it's got a weight. And obviously passengers, payloads, etc. are going to also add to it as well. So there's a weight, and there's an upward force that is called lift. It has to be generated to balance weight. So if you're going to be generating more lift, your aircraft is going to be climbing. If you're going to be generating less lift, because weight is going to be the dominant force, we'll move it down. So that's really just about the balance between the lift force and the downward force. So we must make sure that when our aircraft is flying in a cruise, which we call it straight and level flight, these two forces are in balance. Okay. The other two, which we should note, but we're not going to be really considering them today, are these two, highlighted in light blue. Thrust force, which is actually from the propulsion or the engines of different types, and the drag, which is basically a resistant force that's going to be generated. So, as I said, there are different shapes of wings that we can generate lift, but the main lift, as I'm highlighting here, is actually generated from the wing. With the latest technologies, however, some of the recent aircrafts, their fuselage is also contributing into the lift generation. But the majority of the lift that's going to be generated is from the wings itself. Okay, so we are only going to be concentrating on wings today. So look at this Airbus A350. This was taken with a friend in recent Dubai Air Show, so it's actually banking. What we want to do quickly in this slide is to understand what lift force generation is going to be dependent on. So depending on where your airplane is flying, whether it's sea level, it's at a certain altitude, 30,000 feet, for example, the pressure, temperature, and more importantly, density of the air varies. So as the altitude changes, lift force is going to be varying as well, because the amount of air molecules in the air are going to be different. So higher altitude, less air we have, so less interaction between the molecules and the surface. Okay, so this is definitely going to be affecting. The other thing which is affecting the lift is the wing area. So we're talking about aerodynamics. It's the interaction between the flow and the solid surface, in this case wing. So the larger the area, the more interaction we're going to have. And if the shape is right, you're going to be generating more lift. So the larger the wing area of your airplane is going to be giving us more lift. So lift is proportional to this area. The other parameter is airspeed. So the lift force is also proportional to airspeed. Okay, it's not linear, but it's proportional to the airspeed. So the faster the speed, more lift is going to be generated. The last but not least is the actual characteristic of the wing itself, and that's what we're going to be concentrating on. Okay, so the characteristic of the wing, which are basically the profiles of the wing, like the one that you can see here, is basically determining how much lift is going to be produced. Okay. So, as I said, today we are looking at a rectangular wing. Looking at this image, if the wind direction is going to be from the bottom to the top of the slide, this part here, this line is going to be called leading edge. This is the basically this part here that is first seeing the flow, and then we're going to have the aft part, which is called trailing edge, and that's where the airfoil finishes. The distance between the leading edge and trailing edge, so the distance between leading edge and trailing edge, is called chord. And the distance between the two sides, like what we have here, or these two sides, is called span. Like the aircraft model we have, it can have a long span, or like the airfoil we have, just it's been designed for testing, you're going to have shorter span. So span can vary. Okay, and obviously this section is going to be the wing area. So if you look from the top, this is exactly the direction that you're looking at through the camera. This is going to be the wing area. That's going to be very important for us, as we said. Okay, so in theory, and in fact that was the type of airfoil that very long time ago was first produced, if you're going to have an airfoil which is basically a cross section of the wing, so if I cut the wing at certain point, so the shape that you'll see from this side is called airfoil. It's a teardrop sort of geometry. Then if the center line, which is basically running through here, divides your airfoil into two equal parts of upper and lower section, this airfoil is going to be called symmetric airfoil. With a symmetric airfoil, if you place it into the air, either move the airfoil or run the flow to go over it, since there's a symmetry with respect to the horizontal axis. The force that's going to be generated at the top, it's going to be equal to what's at the bottom if you're going to be holding your airfoil horizontally. It means there's not going to be any angle between the line that is connecting your leading edge to the trailing edge, which is your chord, like what I'm showing in this slide here. And hence, these two forces are balancing each other, so no lift is going to be produced. So what do we do to generate lift for symmetric airfoils? We change the angle. So we change the angle of the chord with respect to the horizon, or with respect to where the flow is coming from. And that angle is called angle of attack, where the higher the angle, the more lift is going to be generated from the top. It's because the projected area of the upper surface is going to be longer than the lower. Flow travels faster at the top, hence the pressure gets smaller. Less pressure on the top than the lower, there's going to be an upward lift generated. Okay, so with the symmetric airfoil, the only way we can generate lift is by adjusting or changing the angle. So look at this slide. Top left shows a numerical simulation where the lift is generated. The bottom right is actually a graph which soon you're going to be generating as well. It's a lift force as a function of the angle of attack. So the higher the angle of attack, more lift is going to be generated. So the higher the angle of attack, more lift is going to be generated, but the flow around the airfoil is going to be becoming more complex, and you're going to start seeing separation of the flow. You're going to see turbulences, eddies, vortices, all of this sort of messy flows like what you see, in blue regions in this simulation, that will at some point stop increasing the lift. So that point onwards, no matter how much more you increase the angle, since there's not going to be any flow attached to the surface, it's going to be separated. This upward lift is not going to be sufficient. The weight will dominate and your aircraft will sink basically. So this phenomenon is called stall. And you would see in this graph where the peak is where the stall is actually happening and the separation is going on. So the question would be, what are the other ways that we can generate lift? One of the common ways is to adjust the geometry of the wing itself. So we create the curvature that by adjusting the angle we give ourselves. So looking at these graphs, what basically we're saying is what we bring asymmetry into our geometry. So basically we'll curve the chord line, if you like. So we change the balance of the area between the upper and lower section when the chord runs through the leading edge and the trailing edge. So the asymmetry and the curve is called camber. Okay, this is called camber, and obviously you can have different curvatures to be able to generate different lifts. Okay, so one of the main parameters in airfoil design or wing design is adjust the camber, and that's what we're going to be actually doing today. Okay, today one of the tasks we're going to be following is adjusting the camber to be able to produce the amount of lift that's required to hold an airplane in the air, basically. Okay, so the other thing that we are going to be using with the terminology is the thickness. We talked about camber, it's going to be called thickness. So the spacing between the upper and lower, or the distance between the upper and lower surfaces, is called thickness of the airfoil. And obviously it varies, but there's going to be a point that you get a maximum point for the thickness, and that's normally what we define. and that's a percentage of the chord. So if the chord is from 0 to 1, will, depending on the design of the airfoil, we can say, oh, the maximum thickness is going to be, let's say, 25% or 0.25 of the chord, for example. Okay. So just to summarize the terminologies that we have actually learned: the lift force, which is generated by the wings; the span, the distance between the wingtips; chord, the distance between the leading edge and the trailing edge, right? So distance between trailing edge and leading edge. The airfoil, which is basically the cut two-dimensional section of your wing. And in real wings, it can vary. The actual profile can vary. And this is basically the secret of the companies. And then we talked about the camber, the asymmetry between the upper and lower surfaces, and the thickness, which is obviously the distance between the upper and the lower surface for certain location along the chord of the airfoil. Now let's look at the tool. It's been designed by NASA. It's called FoilSim. It's a simulation tool, and it's used only for educational purposes. We can't use them for any real projects. So please note that, and that's actually been made clear by NASA themselves as well. But it's a very powerful tool, easy to use, to be able to demonstrate everything we just said. So, looking at my slide, I'm going to be showing you a live demo in a second, but I thought it would be easier if I show you the different sections of the tool. So, the page is divided into 4 sections. Okay, so 4 sections. The top right are where we select options. There are certain input options for us and certain output. So the input is in blue, output is in red. I'll show you when I'm demoing live. And these are basically the final outcomes. So the lift force, for example, the drag force, it gives you the drag as well. We're not looking at drag today, but the tool will provide you with the drag force. And then the normalized lift and drag, so it's called lift and drag coefficients. And obviously there's a Reynolds number or lift to drag ratio, which we can discuss them later. It's not actually the subject of this episode. So the other thing you have to be then careful is going to be the units of the parameters that you want to use. Either you want to use metric or you want to use British. For this episode, we're going to be all using metric units. So the first thing you do when you open it, it might be already in British unit. So you just change it with the drop-down menu selection into metric. Okay. Then the top left is a contour or visualization, basically a panel or window that will show you your geometry. It's not only airfoil. You can choose different shapes, as you can see here. We can choose circle, ball, sphere, ellipse, for example, or even a flat plate. Today we're going to be using airfoil. And then the bottom left is still some extra adjusting tools, adjusting variable tools that we can use. And the bottom right is going to be the graphs that the tool is providing us. Okay. So just to get a bit of feeling of how the tool works, I thought it would be useful if we can have a practice example, and we are then going to be able to understand how we apply the knowledge or the values that we have into the tool. Okay. So here is the question. We have an airplane. It's flying a 45,000 Newton weight. So remember the straight and level flight? For us to be able to fly an airplane at certain altitude, the lift and the weight must be the same. So when it says there's a weight, and I'm using W here for the weight, is such and such Newton, it's a force. It means the lift that the wing has to generate should be the same as that to be able to fly straight, as we mentioned earlier, right? So we want the airplane to fly at an altitude of 2,000 feet, which is equivalent to 600 meters. We know that the wing is at 5 degrees angle, so it's not horizontal. There's a 5-degree pitch of angle. For this particular airfoil, the camber is 8.8%. Okay, so that's where the maximum camber is in percentage of the chord, and the thickness is 15% as well. So the maximum thickness is occurring at 15%, and the area is 8 meters square, right? The question is, what airspeed this aircraft should fly at to be able to meet these conditions? Okay, so the airspeed is the variable parameter for us. So let's then move to our browser where we have the tool. The first thing we do, let's reset to make sure that we're starting fresh. As I mentioned, the units, I'll change it to metric. We start from left for the inputs. The tool allows you to choose different locations like Earth, Mars, even changing the air into water, and even Venus, for example. So we obviously are using Earth. The airspeed is the one that we're going to be varying. Altitude, we already set 600 meters. Okay, so I'll choose that. So you just need to move the slider. There's nothing else we can choose here, or we can vary. The shape is already airfoil, so we don't have to change it. The angle, we set 5 degrees, so I'll drag it until I get 5. Camber was 8.8. Okay, and the thickness was 15%. Okay, so we're going to have a camber at 15%. There are some built-in options, so if you want the symmetric airfoil to start with, high camber, etc., you can also choose them if you wish. So you can see by adjusting these angles, the values of lift and drag are changing. Okay, and we do get them in the graph, and this is actually force, so they're in Newton. In the analysis, there are certain settings that you can change. We're not going to be really talking much about them today in this episode, but you can make some adjustments for some of the parameters. You can choose the plots that you want to actually show. You can have lift versus angle, I was just telling you, or you can have pressure, velocity, any other combination, which I'm sure you can explore yourself. The last input option is the size. That's where we have the lift. This is where we have the chord and span adjusted. So for us to be able to get an area of 8 meters square, if the wing wants to be rectangle, we're going to have multiple options, right? So you can have a wing which is going to have a span of 8 meters by 1 meter, for example, chord, or you can have 4 meters by 2 meters. This is where your understanding of different types of airplanes and your design comes into the place. Okay, so longer wings are designed for long endurance flights, for example. Shorter wings are designed for certain missions. So you need to do a bit of research here to be able to understand what wing you want, right? So if your aircraft has to stay longer in the air, you need to have more span. Okay, so you can adjust the chord here, and you can adjust the span. I choose the span as the minimum 5, and if I choose a chord of 1.6, you will see I'll get an area of 8. So that's what it gives me. Okay, now if you look at the lift, we're expected to get 45,000 Newton, but we're not getting it at all. So if you go to the flight section, you realize that the speed is what we didn't change yet. So if your airplane with the current situation is going to be flying at 160 kilometers per hour, it cannot sustain these conditions and it cannot hold 45,000 Newton and it will sink basically or descend. So how would it compensate and generate more lift? Is by traveling faster. So your aircraft has to travel faster. How fast is the question, and this tool allows us to actually find that. So I'll switch to the gauge, and this is the output. If I change it to the gauge, it will show me the lift and drag bar charts. So I'll just start dragging to the right. You can see my lift starts increasing. All I need to do is get to the point where I'm getting 45,000 approximately, right? So you can see around 290 kilometers per hour is going to be the required airspeed that airplane should be flying at. Otherwise, they wouldn't be able to sustain the weight at that certain altitude. It will sink. Okay, so for us to be able to generate certain lift, your aircraft has to fly at certain airspeed. This is with the assumption that the wing has already been designed. So if you look at the shape, we already know what angle we're flying at, we know what camber we're flying at, and we know what thickness the airfoil has. Okay? So now that you have learned how to use the tool, you can work with the tool with different scenarios. So, for example, one is choosing a symmetric airfoil, setting certain parameters, airspeed, altitude, angle. Even you can identify a thickness for your airfoil. Since it's going to be symmetric, I'll start with an easy one. Camber is going to be 0, so it means there's no asymmetry. And you can decide on the area yourself as well. You can say 1 meter square, 2 meters square. And then what you can do, you can start from 0 angle. This is where you're expecting for a symmetric airfoil to get 0 lift, to see actually the tool is giving you that. And then start increasing. Let's say with the increment of 2 degrees, note down the lift, another 2 to 4, 6, 8, 10, and so on. So you can actually see how the lift force generation is happening. And once you have this, maybe let's say up to 20 degrees, you can then use any softwares like Excel or any other software that you use that you can plot the graph. You can explore the relationship between the lift force and the angle. And this is something that you can actually do. The other thing you can work on is, let's say you choose an aircraft, Boeing 737, for example. You would know the maximum lift, or you would know what lift, for example, you want to produce. And you can suggest a scenario. Like, for example, you're going to have sea level takeoff, for example, at Dubai airport. The pitch angle 5-10 degrees you can choose at certain airspeed, right? Then the question would be, okay, for us to be able to generate the lift that's required to lift off the aircraft, let's say Boeing 737, for example, or if it's going to be the cruise altitude, the lift that's going to be required to hold the aircraft at that altitude, right? The question would be, what is going to be the airfoil required to generate that? So when we say the airfoil, the chord is going to be unknown, the span is going to be unknown, the camber is going to be unknown, and also the thickness is going to be unknown. So what you can then do, you can play with these to meet certain design criteria. Like, for example, you can say, okay, I know what the current Boeing 737 area is. So you can start with that and say, okay, if it's going to be, let's say, around 147 meters square, what chord and span I require to have that area. So you can substitute it, you can plug it into the tool, and then you can then play around with the design of your airfoil itself. So you can vary the camber, you can change the thickness, and then you can see you're able to generate the amount of lift that you require or not. Sometimes with the tool you may not, because those aircrafts are flying at very high altitude, high speed. So you can choose a smaller aircrafts like propeller ones, you know, the general aviation Cessna 172 or Bonanza, for example, G36, for example, right? You can choose them, and you can adjust the chord basically on a span to get the area, and then you can get the camber and the thickness to actually find what airfoil is going to be suitable to generate that lift. If you feel you want to look at a bit more realistic scenarios, you can also say, okay, during the phase of the flight, all the phases, weight also changes. So I don't have to actually go with the maximum weight of the aircraft. I can go with 50% of that, 70% of that. That is going to be mimicking certain scenarios, like the cruise, for example. Like when the aircraft is flying at a very light load, for example, maybe there's no full passenger on the aircraft. So the idea is your airfoil and ultimately your wing to be able to generate sufficient lift for all of these scenarios. So that's something you can do by using this tool, which I hope you will enjoy and you will learn more from it.
So now you have designed your aerofoil, and you have, in theory, something that's going to work. But of course, before we use it, we always like to have that kind of experimental reassurance that it's going to do what we designed it to do. And the way we do that is with a wind tunnel. So Mehdi, you have designed an airfoil already.
Yes. So this is the profile of an airfoil, which has been 3D printed
Excellent.
already, and it's going to be mounted on the wind tunnel that we have here.
Okay, so in a wind tunnel then, it has a big fan down on that end there on Mehdi's side, and it's going to drag air from my side here and concentrate it. There's a bit of honeycomb in there, we call that flow conditioning, to make sure that the flow is going to go nice and straight through this profile here. And then by mounting it on this load cell, we're able to measure what?
We're measuring different forces acting on an airfoil. So in this case, we're looking at drag force, which is a resistant force.
So that's how much force that the fluid is exerting on this, in that direction.
On the airfoil. And then there's a lift, which is perpendicular to it. And that's what is used to hold the airplane on the air. So
a non-traditional orientation, you might say here. Normally, your airfoil is going to be in that direction. Yeah. But just because the way our load cell is set up, we're mounting it in this orientation. Exactly. So we could say the force in this direction is our drag, but the force in this direction, kind of away from the screen, is our lift.
Exactly.
Excellent. So let's do the experiment.
Okay, just closing the test section now.
And what we're going to do now is we will set a single velocity, so a constant velocity or wind flow rate through the wind tunnel. It'll make a bit of noise. And tell me then what measurements you're going to take before we create the noise.
Yes. So the load cell is connected to your PC, and this software is basically showing the measurement in the vertical axis as the lift force that we just said. And then the load cell also gives us the opportunity of varying the orientation angle or the angle of attack of the airfoil. So the horizontal axis basically shows that angle for us. So when we change the orientation, that angle is recorded in the system, and we can see it at this axis, which is the horizontal axis.
Great. So you're going to do that experiment for us. You're going to progressively increase the angle of attack for a fixed velocity and measure how does the lift force change as you go.
Exactly.
interesting results here, Mehdi. Again, just to reiterate, on your y-axis here, you have the magnitude of the force, the amount of lift that you're getting from the aerodynamics of the airfoil.
Exactly.
And this is varying against different degrees
Of
angle. So it's our pitch or angle of attack,
exactly.
orientation of the aerofoil. Brilliant. Now, I would have expected, as the angle increased, that so too did the force. And it does, right? At the beginning, it increases as the angle changes from 0.
Yeah.
What's happening here is totally dropped off. What's gone wrong?
Exactly. So what has happened here is the flow is obviously attached to the surface and it's generating the lift. So
it's behaving itself. It's
behaving
in
itself.
theory, the flow is going nice and smoothly over the surface and faithfully following the geometry.
Exactly.
Right.
And as you increase the angle, the flow accelerates further, the pressure drops more, and you get more lift. So that makes sense.
Brilliant.
So there will be a point where the flow cannot sustain this situation. So you cannot attach to the surface. It will going to be separating from the surface, and that's where you start seeing this drop.
And we call this stall, don't we?
Exactly.
This is a stall condition. So we've gone so extreme in our angle that the flow doesn't faithfully follow the surface anymore, and you get this stall. Now, that to me is the difference between what I would call the kind of quantitative measure. I see the actual values of force on your screen there, but sometimes it's kind of, well, we don't fully understand what's going on, and there's more qualitative measures that we can use. And for that, we look to things like flow visualization.
Exactly.
And that's a way of us kind of even just visualizing or understanding what's happening in that situation. So by putting seeding and putting some smoke through the wind tunnel, we're able to track the path of the fluid over the surface.
Exactly.
And then, so we would be able to see in this region here, in these early stages where it's linear, the relationship between the lift and the angle,
Yeah.
we'd see that the flow is nice and smoothly going over the surface.
And as soon as you get close to this stall point,
Yeah.
you start seeing less concentration of the particles or the smokes close to the surface, and you see more of a shadow.
Okay, so that's
so that means the flow is not attached to the surface, and the concentration is moving away from the system.
That's kind of where theory breaks down in a way, right? Exactly. Because those equations that we use in our simulations, those equations that we use to design the kind of the fundamental geometries, no longer apply in that scenario because
Exactly.
it's not doing.
It will apply up to this point where you don't have separation.
Excellent.
After that, you can apply the same exact.
And these are one of the huge values to be an engineer. We need to be able to apply theory. We also have to understand when theory applies and when it is less simple. And we need to be able to design around those scenarios. And there's lots of different added extra geometries that you can put onto this to avoid these conditions of stall. But fundamentally, it all goes into what can be a complicated three-dimensional design. I hope you have managed to get some insights in some of the challenges that and some of the opportunities that aeronautical engineers have as and what role they have to play in the future development of what is a very, very exciting industry.
Exactly.